Chapter 1.11.7 System Logs. Summary. System logs capture events within Kubernetes clusters and aid in debugging. Log verbosity can be adjusted for detail, showcasing anything from errors to intricate event traces. Logs do not conform to Kubernetes API stability and may change each release. The Clog library generates log messages for Kubernetes components, and as of version 1.23, Kubernetes started adopting structured and contextual logging. While some Clog flags are deprecated, logging now supports storing logs as JSON, allowing easier data processing. Logs from Kubernetes system components are either stored in journaled or .log files in var log. To manage logs, the kubelet configuration must enable system log handling features. This setup helps fetch logs for debugging, especially essential for Kubernetes version 1.30. System logs. Logs are crucial for tracking events in a cluster and help in debugging issues effectively. You can adjust the log verbosity to view events either in broad strokes or in detailed steps, such as HTTP logs or component actions. However, note that the structure and content of log outputs are not stable across Kubernetes releases, meaning they might change with each update, unlike command line flags that remain consistent. Clog. This code is a log entry indicating an HTTP GET request made to the metrics server pod in the kube system namespace. It shows the timestamp of the event, the duration of the request, 1.512 milliseconds, and a response code, 200, along with other details like the user agent, platform, and client IP address. This code snippet shows a log entry with the timestamp I-10-25 0 hours 15 minutes and 15 seconds. 525108, indicating the date and time of the message. The number 1 after the timestamp represents the log level, and example Go 79 indicates the file and line number where the log was generated. The message itself says, "This is a message which has a line break." This code represents a log entry generated by the Clog framework. The header includes the timestamp and file location of the log message. The message is followed by key value pairs that provide additional context or information about the event being logged. This line of code indicates that the controller _utils Go file logged a message at the timestamp 0 hours 15 minutes and 15 seconds. 525108, stating that the status of the pod named kube system, Kubens, has been updated to ready. This log entry is from a file called example. Go at line 116, indicating that it is logging an example message. It includes data with a line break and quotation marks, as well as some int, some float, and some struct values with specific values assigned. The some struct value is a structured data type with string field having 2 lines of text. The code snippet shows the usage of a command to run a Go program that displays logs with contextual information. The output includes log entries indicating runtime information such as the logger, duration, and other details related to the example program being executed. By setting the feature gate for contextual logging to true, the logs will include additional contextual information for better debugging and analysis. The code snippet runs a program with the flag contextual logging set to false, which disables contextual logging features. The program outputs log entries showing runtime information with different durations for 2 separate events. This code snippet is a JSON log entry indicating that the status of a pod named Nginx1 in the default namespace has been updated to ready at a timestamp of 1,580,306,777.04728 with a verbosity level of 4. Clog is the Kubernetes logging library catering to system components in Kubernetes. Since Kubernetes is working on simplifying logging, various Clog command line flags such as logtestdir, logdir, among others, have been deprecated starting with version 1.23 and fully removed in version 1.26. although output redirection is expected to be managed by the invoking component. The kube log runner binary serves as a wrapper to redirect output for scenarios where typical methods are unavailable, like on distroless or Windows systems. The transition from traditional clog native format to structured logging began in Kubernetes version 1.23 as a beta feature, allowing uniform log message structure for easier and cost-effective processing. However, a warning is issued that not all logging is structured yet, and changes in formatting or serialization might occur. Structured logging primarily retains backward compatibility, meaning log information can sometimes continue on the next line due to data volume. Introduced in Kubernetes version 1.30 in beta, contextual logging extends structured logging's capabilities by adding context through functions like with values or with name, enhancing flexibility. This approach allows developers to pass additional data into logging functions, even if the function itself doesn't get modified. However, when contextual logging is not enabled, calls revert to global clog logging, omitting additional data in logs. The JSON log format available as an alpha feature starting from Kubernetes 1.19 allows logs to be written in JSON instead of traditional formats. Note that standard clog flags might not support JSON output, and some logs might remain in non-JSON format, especially during initialization. This format uses specific keys like TS for timestamps and ERR for errors, impacting components like the Kube Controller Manager and Kube Scheduler. Log verbosity, controlled by the V flag, adjusts the number of events logged based on severity. A higher V value increases logged content to lower severity events, while a setting of 0 logs only critical incidents. The location and method of storing logs differ based on whether components run in containers or not, with log files typically found in var, log and systemd handling logs for non-container components. Log rotation, configured with logrotate, also accompanies these setups. For Kubernetes environments set up with the kube-up.sh script, logs are managed with the logrotate utility configured to either daily rotations or upon exceeding 100 MB size limits, ensuring consistency and availability in log management across Kubernetes nodes, emphasizing efficient data handling and organization. Log query. The code fetches the kubelet logs from a node named node1. Example using the kubecl command with the raw flag to make a direct API call to the node's logs endpoint with a query parameter for kubelet. The code retrieves the logs of a specific node in a Kubernetes cluster by querying the log file specified in the query parameter. The node name and log file name need to be inserted into the command for it to function correctly. The code fetches the kubelet logs from a node named node1. Example, filtering for logs that contain the word error. Kubernetes version 1.30 introduced a useful debugging feature for nodes, although it's disabled by default in beta. This feature, from Kubernetes version 1.27, provides the ability to view service logs on nodes. To utilize this function, you must enable the node log query feature gate for your nodes. Ensure that the kubelet configuration options enable system log handler and enable system log query are set to true. Service logs on Linux are typically available via journaled, while Windows uses the application log provider. Logs are also accessible in the var log directory on both systems. With the right permissions, you can access logs from all or selected nodes. To fetch service logs like kubelets, logs must be in a directory kubelet permits access, like var log. The kubelet checks logs using heuristics, starting with the native logger and then var log directory paths. This aids in retrieving logs for debugging even if you're unsure of the logging method used by services.